Boom. Hello and welcome back to Calculus 1. We are starting chapter 3, but this first lecture will have actually a lot of chapter 2 limits calculations. Before we start, I will remind you of a few things. First, I will say that we have to consider left and right limits so that we know that the overall limit is what it is or does not exist. Also, need to remind you that if you get 0 in the denominator when you plug in values, you have to worry about algebra or some other method. You can't use plug-in method. So if I have limit x goes to 3 for x squared, yeah, that's 3 squared is 9. So plug-in method for something like this works. But if you have limit age goes to 0 of, let's say, x squared minus 3 over age, whatever, you can't plug in. So cannot plug in. So we need a graph or something to figure these things out. So that's the first part. And now also remember that the formula for slope in algebra was y2 minus y1 over x2 minus x1 when you have 2 points. So x1, y1, and x2, y2. So slope, m. These are the things we need. The rest we can figure out. So let's talk. First graph is going to be a function f of x, and I am going to pick 2 points P and Q, and you see that the point P will have x1, y1, and point Q, x2, y2. This line would be called a secant line. In Greek, secant means to cut. This line cuts through the function, so we call it a secant line. So the slope would be m secant, and so secant line, and the slope over here is y2 minus y1 over x2 minus x1. So this is algebra. This was actually the part of your 2.1 before we did any limits or anything like that. Now I'm going to do something here. I'm going to allow this Q to travel alongside the line towards P. So P is going to be fixed point, and Q is going to move. Now P is going to have our A, f of A coordinates. So P has your A, f of A coordinates. You are given function f of x. If you plug in A, you will get f of a out, right? Now your q, remember, q is the one that moves. So its x coordinate must be x, because it's supposed to take on all of the values as it travels towards P. So this x goes to A. See that? X goes to A. That's nice, right? X goes to A. We heard this wording before. So now what's happening here? I can draw a secant line in between, right, that connects P and Q. You can extend it if you want to, you don't have to. And then, good effort, Q is going to move to the new location. Call it Q1 location. Q star, Q prime, whatever. And you are able to use algebra again to find the slope of the secant line. And the Q moves again. And you are able to find, using algebra, another secant line slope. So I hope that you would agree that as the Q progresses towards P, changing its location, anytime when Q is at one of the points, you can always use secant line to compute the slope. You can always use the slope formula to compute the slope of the secant line that connects P and Q. So what are these 1, 2, 3, 4, 5? Those are just instances in time, because Q is moving, and as the Q is moving, every time there is a there are new coordinates x and y for Q, and you can use those up there to calculate it. So what do I have? I have that the m secant is y2 minus y1 over x2 minus x1, but we know that the secant is f of x 2 minus f of x1 over x2 minus x1. So we get to use these x's rather than to use x and y, because we have a function defined, and we can always compute y's by plugging in x values. So calculating m secant is going to be expressed in terms of this. Now, what I'm going to do is I'm going to fix these x's into y2. So this is my x, a, x, and a. So I fix them because instead of using x1, y1, and x2, my points are labeled as a, f of a, and x, f of x. So instead of using y1 and x1, I'm just using what they're supposed to be, a, f of a, and x, f of x. And there it is. So this is our official m secant using just algebra, written in a language of functions, or pre-calculus, right? Where you have f of x minus f of a over x minus a. So that is nothing new. You know how to compute the slope of the line when you have 2 points. Now, what happens when Q and P collide and they are at the same point? We get still a line, but now we can't use algebra to compute it, right? We can't use algebra to compute this, because when you look at it, there's only one point because in this case x is equal to a, because q is with p at the same position. Wouldn't that give you the denominator to be x minus a as either x minus x or a minus a, whatever, is 0? So in this case, algebra fails. Okay. As every other problem in life, just walk away, because this is terrible case. We were able to compute all of the slopes, all of the infinity of the slopes coming up to point P, and all of a sudden, denominator is 0, can't compute the slope, just leave it alone. Skip it. And as the point Q emerges on the other side now, over here and over here and over here, we still have these secant lines. So we have infinitely many secant lines before we hit this special red line. And then again, after that, there are still infinitely many blue secant lines. And we can calculate this infinity of these lines one by one, because we have our algebra formula. Now, are we happy with that? We are able to calculate infinitely many cases. No, we just want that one. That one we can't compute easily. That's the one we're interested in, right? Such is life. Right? Grass is always greener on the other side. So, what would be the way to compute that one case? To find the limit. Very good. The concept of the limit says, compute infinitely many from the left, infinitely many from the right, and if they all scream the same value, the limit exists. So, this special line is called the tangent line. I heard it. Great. So, M tangent, which is the tangent line, slope of the tangent line, is the limit as x goes to a of m secant, which is limit x goes to a of f of x minus f of a divided by x minus a. So this is the way to compute, but now we're not really happy because it's just way too many things to worry about. So let's make it better. So guys, this is a concept over here, not what you would use for calculations. This is just a concept to understand that the slope of the tangent line is the limit of all slopes of the secant lines as they as x goes to a. So now, to fix this, we're going to say let x minus a be equal to h. That's a substitution. Substitution. And now, plug in. So what do we have? M tangent is going to be limit x goes to a, we'll fix that, of, and now I want to eliminate these the x's, right? So if I want to eliminate an x, then x is equal to a plus h. So plug that in, and instead of f of x, I have f of a plus h. Minus f of a, that has no x, divided by x minus a is h. Do we see it? Do we see the formula? You remember the formula? Yeah, it's a difference quotient, right? Except it's with a's rather than x's, but we'll fix that eventually. Do we all see the issue? We're not done yet. The trick is to subtract a on both sides. And when you subtract a on both sides, you get x minus a goes to 0. But you know that your x minus a is age, so here's your age goes to 0. Yay! M tangent now is given as the limit. Age goes to 0 of f of a plus h minus f of a over h. Box it. Then highlight it. And then use another 2 colors. And green. Do we need orange? Yeah, we need orange. And put this. That's good enough. Yeah, I'll put one. One more. I'll add on top. They're just sine functions. Alright, so absolute sine functions. This is the way to calculate slope of the tangent line. Let's calculate one. Or 4. Find the slope of the tangent line at x equals 3 for f of x, x squared minus 2, whatever. Okay, all we need to do is to compile. First off, we know that this 3 is your a. Which is this a over here and this a over here. That's the 2 a's. So we compile f of a plus h first. It's a plus h squared minus 2, which is a squared plus 2ah plus h squared minus 2. And then now that we know that a is 3, so f of 3 plus h is going to be 9 plus 6h plus h squared minus 2 for a total of 7 plus 6h plus h squared. So what have I done here? Recalc1. That's what I did. I have the function. I need f of a plus h. So every x will be replaced by a plus h. You see, between these two, that you have x matches x, square matches square, minus 2 matches minus 2. Do we all see that? Great. Now, distribute, copy 2, and now we plug in a is equal to 3 because that's given to us. A is 3, there's your a, there's another a. Combine all the arithmetic and we finally have this. So, M tangent is going to be limit as h goes to 0 of f of a plus h, so it's f of 3 plus h minus f of 3 divided by h. Well, we have all of these, so just plug them in. F of 3 plus h is 7 plus 6h plus h squared. minus f of 3, that's going to be 3 squared minus 2, divided by age. How much is 3 squared minus 2? Very good. Those cancel. And all we have left are terms that have age. So factor 1 age, 6 plus age left, divided by age. These drop. Age goes to 0 because age goes to 0, and your answer is 6. So m tangent is equal to 6 for x equals 3. There's the calculation. And this is your 2.3 homework, this calculation. It wasn't homework. We did not use any new techniques, any new methods. We did not define anything new. This is what you're supposed to do in 2.3 homework when we did algebra limits. What was algebra here? Well, first off, you had function composition, and then your algebra was to cancel these and then factor one of the ages. Right, so factoring and then calculating. So no calculus until you reach the last step when you say, oh, age goes to 0, so your age goes to 0, and the slope is, so it turned out to be 6. This is the point to say, I didn't want actually x goes to 3. I want x goes to -2. So I still have f of x as x squared minus 2. But now I want x equals -2, not 3. So what's the m tangent now? We have to do everything from scratch. The whole calculation. Because we have to find f of -2 plus age first. And that's going to be -2 plus age squared minus 2. Work that out. And then do the entire limit. There's going to be 4 minus 4 age plus age squared minus 2. So f of -2 plus age is 2 minus 4 age plus age squared. Plug everything in. Limit age goes to 0. F of -2 plus age minus f of -2 divided by age. So how much is this? That's 2 minus 4 age plus age squared minus, and now we have -2 squared minus 2 over age. Limit age goes to 0. 2 minus 4 age plus age squared minus, this is 4 minus 2 minus 2 divided by age. These guys cancel, and you see that the only terms that are left up there have age. So you factor age, you are left with -4 plus age divided by age. So these drop, and this one goes to 0 because of the limit, because age goes to 0. As soon as you remove the denominator, you can immediately go and say goes to 0. So now the total is negative 4. So slope m tangent is equal to negative 4 for x equals negative 2. So we have obtained another slope. So over here we had m tangent was 6 for x equals to 3. We did 2 of these already. But I really don't need a negative 2. Actually, I need a 10. We have to restart the entire calculation and grow through the entire grind, right, all of this, to get the answer at the end. Is there a better way? Is there a way to compute all of the slopes and then just plug in the particular one I need and get that one at the end, rather than restarting this procedure for every single slope that I have to compute? So our old formula for m tangent was limit h goes to 0 of f of a plus h minus f of a over h. That's the old one. What should we change for the new one? What should we change? Remember that a is a particular value and you have to plug that value in. And that's exactly what we are trying to avoid. So how should I modify the formula, the upper formula, so that it's easy for us? Change a to x. F of x plus h minus f of x divided by h. And here is your boss equation. Barbed wire to protect it. Add some blue for color. It's like, mental something. Complementary orange. Provides another layer of barbed wire to protect this formula. So this over here is your boss equation. What does it calculate? Let's check. Go back to our problem. Find the slope of the tangent line at x equals 3 for f of x equals x squared plus minus 2. Instead of using x equals 3 as 3 is equal to a, we are going to ignore that. And we are going to compute the general formula first. So my f of x plus h is going to be x plus h squared minus 2. And that is x squared plus 2xh plus h squared minus 2. There's nothing, you can simplify there. That's it. So what we do is we plug all of this into limit. Limit h goes to 0. You know what, I'm going to write the formula first. F of x plus h minus f of x divided by h. So what do we have? We have the limit age goes to 0. We have x squared plus 2x age plus age squared minus 2 minus. And now I have f of x. Well, that's just the original function, x squared minus 2 over h. Limit age goes to 0. Get rid of the parentheses. What do we have? X squared plus 2x age plus age squared minus 2 minus x squared plus 2 over h. This is your checkpoint, because all terms that contain, all terms without age have to cancel. You can't just remove them. They have to cancel. If something is not lining up, it's wrong. So that's why it's called a checkpoint. All of the terms after cancellation that survived have age in them. So factor out age, 2x plus age over age, and now finally the age in the denominator is gone. As soon as that is there, we have limit age goes to 0. Of 2x plus age. This is where age goes to 0, and we get 2x as the answer. So, what is 2x? What does it do? That's what I'm interested in.
Yeah, it's a slope of the tangent line.
Is it? Not slope. It's related to it.
Is it perpendicular to the slope?
Nope.
Parallel?
Nope. None of that. None of those geometrical properties. It's related to the slope, but not in the way you think. You're thinking geometrical and things. What is the what would this do? What does it do in terms of our problem? Remember that we have x equals 3 on top. So when you plug that in, what do you get? You get 6, which is right. We did that with when we did the age method, right? Do you see that that's a generator? It generates all the values of the slope. That function generates all the slopes. You give me any x. You want that -2?
Sure. Yes.
What's 2 times -2? -4. Look at your notes. What was the slope for -2? It was -4, right? Magic. So, this 2x is a function that will generate all values, all slopes. And we just have a special name for that function. We call it the derivative, yes. So what is the derivative? It's a function that generates all slopes of tangent line. So what is the central problem of derivatives? It's actually the slope of the tangent line. Why? Because it measures the instantaneous change. And I have to explain that. But as you can see, the calculation, right, the brute force calculation is your 2.3, right? And we just have concepts on top of that in this lecture. So let's go and write some stuff first of all. So this function. This function will generate all tangent line slopes. Now, it always breaks my heart when you are not excited about this. Not because it's calculus, but because for years up to this point, you were told that you need 2 points to find slope of the line. Now, you give me x equals 3, I tell you that the slope of the tangent line is 6 because I plug in 3 in there, right? Was this 2 points? No, it was 1 point. You need to be excited about this because you can find the slope of the line with 1 point, right? That's amazing. Rejoice quickly. Oh, you're terrible people. X equals -2 from before. M tangent, -4. I was talking something about 10. What's the tangent? 20. Double it, right? Yay. No?
So to find this function, you just
this. So we did the procedure. Here's your difference quotient. What happened?
Is it a composite function?
Yes.
Okay.
So now, this is called derivative. So what is the derivative? The derivative is the function which generates or gives all possible slopes of the tangent line in the domain. That's what the derivative is. Now, on a scale of importance of this tangent line and the slope of the tangent line, if you go on a scale 0 to 10, this is about 536. All right, on a scale 0 to 10. Because it measures change. Your speedometer in a car is this. What happens to the needle that shows your speed? As soon, instantly, as soon as you touch either gas or a pedal, either gas or a brake pedal, it moves, right? It shows instantaneous change in speed. Acceleration makes you go faster. You push gas pedal. You push brake. It makes you go slower. Now, your speed is measured in miles per hour. We are going to have a full lecture on this in chapter 3, on speed and acceleration, all of these things, right? But now, just to understand how important this is, you have miles per hour to be your speed. We'll talk about velocity and other things next time. So miles per hour is your speed. When you look at this thing, the speed tells you how far you're going to get in 1 hour. So 60 miles per 1 hour means what? We will go 60 miles in 1 hour. Right? That's it. So when you are on a 65 mile per hour highway, and let's say you are driving 60, don't, you're going to get wiped. Right? There'll be a truck going 80. Don't. But if you're on a highway driving 60, and New York is 60 miles away, that means you'll be there in 1 hour. and it will take an hour to come back. If something is 300 miles away, you're driving 60. What is the 5 hours, right? If you are driving 60 miles per hour in this special car at the path that is the orbit of the Earth around the Sun, how long would that trip take? 60 miles per hour. I mean, you can't drive 60 miles per hour in the neighborhood, right? It's a huge speed, is it? 60 miles per hour is a huge speed. We have a speed limit. You come to the parking lot outside, it says 15, right? 15. You drive 25, let's say you're 10 over. So now we have to take away your car, your phone, your dog, right? And you pay the fine. You went 10 over, right? 60 miles per hour orbit of the on the path that Earth takes, the orbit of the Sun. How long does it take? No one knows? It takes 1,111 years. That's how pathetic 60 miles per hour is. This is how insignificant we are as a species. Right? It starts raining or snowing, you can't get to Somerville from here. Right? In like 7 hours. To drive once around the Sun on the path that planet takes, it would take 1,111 years to go around once. The planet will catch up and crush you 1,111 times. That's how fast. So that's your 60 miles per hour, and that's how far we got as a species, right? What's Agdil? Agdil is just a potion that is, right? Supposed to make you better. Nothing. So the derivative, this tangent line, is instantaneous change. Change at the single point. You touch gas, you touch brake, speed changed instantly. And that speed is how far you go in time that elapses. So we figured out teleportation on a very basic level. Scientists were able to teleport a particle right across the river. Great. Now we have to do that many times in order to teleport, right? So the next thing is, let's try to teleport a virus or a bacteria or something like that, right? Eventually, if we don't blow ourselves up, teleportation would be something, or it still is not instant. It happens in time, because if information travels at speed of light, that's how fast you get to teleport. So these derivatives, they measure the change in time. For instance, I already said this, but here it is again. You are the tallest when you wake up in the morning, because you were unconscious in a horizontal state, unless you sleep against a tree or something weird, but people usually sleep in a bed or something. So if you are horizontal, your joints and everything relaxes, you stretch. When you wake up in the morning, you're the tallest for that day, then your body weight is going to slightly compress all of your joints, and you have a lot of them, right, in the hips and your knees and the ankles, right? They compress. They don't compress 3 feet, right? They compress a tiny fraction of an inch, but you are shorter for that much at the end of the day. You only grow in your sleep. It's very simple. So now, those changes can be measured by the derivative. It's instantaneous change, because It is not that you got up and everything compressed. Right? All of this happens over time. It's constantly changing. And if you pick up something heavy, it's gonna change faster than if you don't pick up anything heavy, right? It should be common sense. So, how much faster are your joints going to compress if you pick up something heavy than if you don't? Measured by the derivative, right? So these are the things. Calculate how fast the rocket fuel is going to be used up, burned up. So when you fire a rocket, right? Because the weight of the rocket is important. The same thing goes for your car and the fuel in a tank. As you drive around, the you plus the car, in terms of the weight, is lighter and lighter and lighter as you are converting that gas very inefficiently into motion forward. So all of these things are measured by the derivative. And all we care about is the tangent line, because tangent lines slope. The steeper the tangent line, the faster the change. The slower the tangent line, right, the less steep the tangent line, the slower the change. So, if the population is falling off like this, versus population falling off like that, this is much bigger panic. This is all happening in time. And the population, let's say, of a nation. We did talk about Japan. You pick a point in time t1, and you see your tangent line is like this, and you pick the same t1, same year, and the tangent line is like that. So one tangent line and the other tangent line. You see that this one over here is steeper. Meaning more loss if this is loss of population, right? So these tangent lines are what we are after, the slopes of these tangent lines, because they measure how fast you are gaining or losing stuff. You can be gaining or losing money on a market, and all you look at are the tangent lines, because it tells you the rate at which you are gaining and the rate at which you are losing. It's the rate of change. And we are going to have a special lecture for it. It's not going to be the same as average rate of change. We'll talk about that when we get there. So now let's practice more of these limits. No more concepts. The only concept here was that you get to use the function and 1 point to calculate the slope of the tangent line rather than using 2 points as an average. So now find the derivative of f of x equal 1 over x. Well, you have to plug that in. Limit h goes to 0, or f of x plus h minus f of x over h. So as you can see, calculation is 2.3. The only thing that we introduced now is said, okay, let's call that homework assignment the derivative. So now you had a homework assignment with 1 over 5. And we might even have done that in class. With 1 over 5 here. Now I'm asking the same problem with 1 over x in general terms. So let's see what you come up with. So in the textbook, you have this problem on page 80, problem 40, and it's not 1 over x, it's 1 over 5, but it's the same calculation. And there are more, more different quotient ones. This one is actually exactly what I'm asking here. All right, let's take a look at this together. Then we'll do something with square root or something. So, we first have to compile difference quotient, which means I need this piece. So f of x plus h is 1 over x plus h. That's as simple as it is. I'm replacing is x with x plus h. So now, I plug everything in because I just got this. This is just 1 over x and h is h. So we have everything. So limit h goes to 0. 1 over x plus h minus 1 over x over h. Limit h goes to 0. And then we cross multiply over here to get the common denominator of x plus h. So this is x minus h, because it's a negative. So x times 1 is x, and then x times negative 1 and h times negative 1, divided by h. Note that my middle line over here is longer than the upper line, because that's the main division line. You can put over 1 if that makes it easier for you to compute. So this is now limit h goes to 0. We have these x's drop, and you are left with negative h on top times this 1. So we just have negative h. And on the bottom I have h times x plus h. If you are not remembering, and you should because I know we reviewed it, you multiply two that are close by, you put it down, and you multiply two that are far apart, and you put that up on a fraction. So negative h times 1, it goes in the numerator, and then the two middle ones, right? It's h times x plus h that goes in the denominator. Now this h drops, leaving negative 1 on top. So I have limit h goes to 0, negative 1 over x plus h. The h goes to 0 because h goes to 0, right? And all you're left with is negative 1 divided by x times x is x squared. And there it is. So we say if if f of x is equal to 1 over x, the derivative f prime of x, that's the notation, is negative 1 over x squared. Now you provide me with x value. I will give you the tangent line slope instantly. 3, negative 1 over 9. Half, negative 4. Right? Whatever value you give me, I immediately plug that for x, and I compute the tangent line instantly. So derivatives are good to have because they give you the slopes of tangent line. And what is the tangent line measure? As we are going to see, it measures the instantaneous change. So we can calculate in a population how many did we gain or how many did we lose in a particular year, because a year could be thought as the incremental instance in time. So that's all coming up. You will understand that as we move on. This section again, we only introduce the derivative and we work mechanics of limits. So find the derivative of f of x is equal to the square root of x plus 3. let's at least set it up, and then you can work on calculations. We know we need f of x plus h, so that will be a square root of x plus h plus 3. Right? That's that. And now we have the limit. H goes to 0. Square root of x plus h plus 3 minus square root of x plus 3 divided by h. What's the only thing I can do here? Yes, conjugate, which is rationalized. Yep. So we have x plus h plus 3 plus root x plus 3 divided by the same thing. And then you just grind through algebra. Let's see how that goes. And please don't trigger my allergies by not writing the limit on every line.
Yes, no.
Let's do this algebra. Right? So what do we have in the numerator? We have difference of squares. If you remember the formula where a minus b times a plus b was a squared minus b squared. That's exactly what we have there. Your a is the first square root, your b is the second square root, and then you have a plus b. So all I need to do is to square these roots, which will kill the roots. So I have x plus h plus 3 minus x plus 3. That's all I have. In denominator, I will not distribute or multiply. I'm just going to leave it like this. And now, if you take a look in the numerator, positive x, negative x gone, positive 3, negative 3 gone. All you're left with is an h. Don't forget the limit in every line until you get to use it in the last step. So we have h, and then h, square root of x plus h plus 3, plus root x plus 3. This cancels. And what do I get? I get the limit, h goes to 0, of 1 over square root of x plus h plus 3 plus square root of x plus 3. Now, h is the one that goes to 0. Everything else stays the same, but this is now 2 of the same that are added. So, 1 over 2 square root of x plus 3. And that's your derivative. So these types of problems are on the page 80 in a textbook. They're in your 2.3 homework on MyMathLab. And now you have a whole bunch of these problems also that you can practice them in 3.1 section for homework, because this mechanic is important in calculations. Now, is this question a possible question on the exam? This particular one. The answer is find the limit. And there you go. Done. I just converted this into 2.3 question. Right? I just need to strike the word derivative out. And it's immediately. Again, these problems are in 2.3 on page 80 in your book, in the homework. Right? And you can practice as many of these as you want. Well, you can there. In 3.1 you can. On page 80, I think you have 2, 3, 4 of these. Something like that. I have root x plus 3 plus root x plus 3, right? So that's 2 root x plus 3. An apple plus an apple is 2 apples. Because there's a plus in between. So it's the addition. Any other questions, concerns? So the rest of this is notation. So, notation. y is equal to f of x. That's your pre-calculus. And now you can write y prime is equal to f prime of x. So that's the function. And that's the derivative. There are other ways to denote derivatives. And in particular, the one way that is better than this one, it's a Leibniz notation. First off, the notation you see over here is the spin-off on Newton's original notation. But Newton and Leibniz derived this stuff at the same time. Leibniz published first, and then Newton freaked out and then published. So Newton did it first, but Newton was like a bad person, like a bad. He was terrible as a human being, right? And he kept the stuff that he was doing to himself. So he invented calculus and then shoved it in a drawer, right? And for him that was an exercise. It was like, yeah, cool, invented calculus, just put it in. It's like, nice. Look at this cool mathematical thing I can do, right? And then when Leibniz published, then he said, hold on, you stole that from me. Well, it was locked in a desk. I mean, no. And then he published, so they have two different notations, right? But they did the same thing. Now, Newton applied his stuff to physics, and that's why he picked up much better than Leibniz, because Leibniz applied his stuff to economics and business. And at that time, right, physics was looked up as cooler, right, thing. Today, it's all about business, right? We have 7,000 business majors and then 3 engineers. So, Newton notation was y with a dot, like that. And then the second derivative, because you can have higher derivatives with 2 dots and 3 dots and so on. So that was that. Now, much better notation. d dx of f of x. This means the derivative in respect to x of f of x, because there is this multiplication that we don't write. So you have the operator which says take the derivative. So technically this says take the derivative of f of x. So this word of is for multiplication. That is there. So we can write in line. We can say the derivative of a square root of x plus 3 is 1 over 2 square root of x plus 3. This is why Leibniz notation is godly. If you want to use the Newton's notation, you have to use 2 lines. You have to say, okay, my function f of x is root x plus 3, and then you have to go to the new line and say the derivative is 1 over 2 root x plus 3. So you either use this as a notation, or you use this as a notation, right? Or you can't mix and match. You can't go in this notation here and say equal and put the derivative, because they're not equal. It's clearly 2 different functions. The function f of x does not have an asymptote, and the one on the bottom does. At -3, right? So you can't put equal in between a function that has vertical asymptote and the one that does not. They have to be very careful about these things. Earlier, we had a problem where we said that the derivative of, and then we had x squared minus 2 was 2x. So this Leibniz notation is amazing because you get to write in line. You know how the limit of something equals limit of something equals limit of something, right? Where Newton's notation over here, you have to go to the new line. And that interrupts the flow if you're doing calculations and things. Good. Other notation for derivatives. Capital D of f. Then you have this squiggly d for partial derivative of f. You have fx like this. What else is there? I already said the original one with the dot. And well, I should add f prime and dy dx, right? If you use that, if you put this, that it's, oh, come on. If you put this equal to y, then you have, and there is a times in here, so that y goes and becomes dy dx. So all of these are different ways to denote derivatives. And as you go through your courses, you're going to see a lot of these. If you have an old-fashioned professor in mechanical engineering, you're going to see this notation. My professor of some of the engineering courses that I took 15 years ago was using the dot notation on derivatives. So it's around. This is used a lot. This is your Calc 3 and this one. Those are Calc 3. It's your linear algebra notation for derivative. So you have your linear algebra. The next two are Calculus 3. The dot one original notation would be something that, now in my class, 90% of the time I'm using this one because I will explain why in detail when we get there, but it's 100% clear what are you taking derivative of and what are you taking the derivative in respect of. So it's the best notation that you can possibly have, and we'll discuss this again. All right, so that's it for 3.1. The calculation is the limit. Oh wait, no, I forgot to say. Yeah, let me add that. For the tangent line, back to tangent line. Tangent line is a linear line perpendicular to the curvature Now I'll have to rephrase this. Sorry, back. Tangent line is a linear line which kisses the function at x equal a and is is perpendicular to the curvature all right. Why are we using the term kisses the function? Well, we are all familiar with the concept of a kiss. There's one mouth, you can kiss one location at one time, right? So that's the first thing. So the tangent line, if you take a look at the curve, when a tangent line goes, it touches at one spot, which is the reason why we use wording kisses the function. Next, that occurs at a f of a, because I used x equals a here. This is your function f of x. Now, what is the meaning of perpendicular to the curvature? Well, when you have any type of a curve, any portion of that curve, you can find a circle that will perfectly fit for just a little bit of the curve. For instance, I am able to fit a circle over here, so if there is a point, there will be a radius, and I have the tangent line. I am able to fit a circle over here. Now this one is big circle, as you can see. It still has a radius coming in from somewhere, and then at that point, tangent line is perpendicular to that radius. So when you say that the tangent line is perpendicular to curvature, it means that you can fit a circle of some radius. This is a terrible circle. And there will be a radius coming in, and there is a 90 degrees from the tangent line to the curvature. Another example which I always give is, and I really hope this never happened to anyone, as you drive in the winter condition, your car wants to go straight all the time. Now, here's a curve, here's ice over here. As the car gets caught in that ice, you are not going to turn, you are going to go tangentially this way, which is off-road. It's a tangent line. It's a tangent line. So this over here is ice. And the motion in that case would not be going where you want to go. It would be the tangent line, which is off-road. That's the tangent line. And this is the green path is the preferred path, but the tangent line is off-road if you slip out. It could be also leaves on the sheet of water in a fall. So that's what a tangent line is. So tangent line is the linear line, right? And tangent line has equation y equals mx plus b, because it's a linear line. And now this m is your m tangent. And this x and a y at a given point. This x is that a, and y is f of a. So we can calculate b. So find the equation of the tangent line, and I'll use what we had before, at x equals to 3 for f of x equals x squared minus 2. Okay, we already have that x is 3. We can calculate f of 3, which would be 3 squared minus 2, which is 7. So I have my point 3, 7, x and a y. Now we know that we calculated the derivative already for this, which is why I picked this problem. We know that the derivative is 2x, which means that the slope of the tangent line is going to be derivative calculated at this x equals 3, so that's 6. So m tangent is 6. So now y equals mx plus b. Y is 7, m is 6, x is 3, plus b. This is 18. So 7 minus 18 is negative 11 equals b. So the tangent line at x equals 3 is y equals 6x minus 11. Note that you have to specify tangent line at the point. As soon you move the point, the tangent line changes. Does that make sense? Of course it's going to change. Because if I'm using x equals 5 instead of x equals 3, it changes everything. My slope now is 10. My y value is 25 minus 2, 23. And these three numbers are going to give different function. So if you change the point at which you are looking for a tangent line, the entire calculation for tangent line has to be redone to come up with a new formula, because the formula is good only at this formula is good only at x equals 3. If you provide me with any other x, I have to redo the same procedure to come up with new x. Well, you're giving me x to come up with a new y and to come up with a new slope, so I can calculate the b. So that's the full problem for to find equation of the tangent line. We can do one more. Oh no, we can't, because you want to go, right? You want to go? So now we're going to wait for a vote. You want to go? All right, fine, you go. Do one more. That's the spirit. Thank you. So that's plus 130 on the next test. Well, I can do whatever I want. It's plus 130. There you go. You never have to show up now. All right, so what do we have? Already calculated. We're just going to do the quick stuff. So find tangent line at x equals to 4 for f of x equals square root of, oh wait, x plus 3. Let's fix this for x equals 6, right? Gives us nice 9. So what do I have? We already have all of the pieces. I have the derivative. We calculated it. 1 over 2 square root of x plus 3. And I have that x is 6. So f prime computed at 6 is 1 over 2 times 6 plus 3. That's 1 over 6. And using this, f of 6 is square root of 6 plus 3 is 3. So just plug everything into y equal mx plus b. You have everything. Y is 3. M is 1 over 6. X is 2. No, x is 6. Plus b. 6 and 6 cancel. 3 minus 1 is b, so b is 2. Tangent line at x equals 6 is y equals 1/6 x plus 2. And it's very fast to find the equation of the tangent line. You need x and a y. X is given, y you can compute from original function, and then the slope you compute from the derivative. So you calculate the derivative, you plug in x value into that derivative to come up with a slope. So I plugged in x is 6. So this 1/6, my slope of the tangent line is 1/6. Right, that's what we have. All right. Bye.
Professor, are these more